Okay, today we're going to take a look at hypothesis tests for population proportion. We'll have two examples to look at today, and we'll also learn how to do these type of problems using the graphing calculator. So keep in mind the overarching idea is that can we use a sample to give us convincing evidence about a population parameter. And today we're going to look at proportions. So here's our first example, and it's about whether Americans look at packaging, nutritional information on packaging. But first of all, we want to take a look at what is the population of interest here. And the population of interest here is adult Americans. So we have a sample of 1,003 from the population of interest. And we want to know if the 1,003, the results we get, provide convincing evidence that more than 50% of Americans check food labels. So first off, let's take a look at some of the data we already have. It'd be natural right now to look at p-hat. 582 Americans in this survey said they do frequently look at the labels out of 1,003, and that's 58%. So it seems like we're over 50%, but is that 58% convincing evidence? Is that big enough for us to conclude something about the entire population? Now, some of the mechanics behind these tests are based on information we've already had about sampling distributions. For example, we know the mean of the p-hats will be about 0.5 if 0.5 is actually the true population parameter. We have information about the standard deviation. Basically, we'd like to know how likely is it that we would get a sample of 58% if the population is truly 50%. Are we just a victim of random chance, or is there a real cause and effect relationship going on here? So that's what we're looking at measuring in this problem. So here's how we step through these type of problems. What we're going to do is we're going to compute something called the p-value here. And the idea here is that we'll reject the null hypothesis if what we observed is very unlikely to occur if the null hypothesis is true. And we'll use the p-value to measure this. And the p-value is the probability of obtaining a test statistic at least as inconsistent with the null hypothesis as was observed, assuming that the null hypothesis is true. So that's a lot to absorb, and we'll do it through looking at a couple of examples here. But basically what we're saying is when we collect 58%, how likely is it that we would get a sample that comes out as 58% if the population is supposed to be 50%? And the probability of that happening is our p-value. And we want to look at that p-value and assess how small that p-value is. Now, how do we measure something being very unlikely? Well, there's a couple ways to do that, but the standard number to look at is 5%. The number we're going to use as a p-value and start to say that things are very unlikely is called alpha. And here we're going to use an alpha of 0.05. But we'll find that in later problems you can use different levels of alpha. But at some point we have to have some baseline for calling something very unlikely. And again, for this problem we'll use 0.05. So let's walk through all the procedures, what we have to do. First of all, the population of interest is adult Americans. Our null hypothesis is that the proportion of Americans who look at these food labels is 50%. But we suspect that it's probably greater than 50%, and that's our alternate hypothesis. We are going to use an alpha of 0.05, and the test statistic we'll end up using is z. Now, we're actually not going to compute this. We could if we wanted to. We've walked through some of these calculations when we did sampling distributions, but we will be using a test statistic, z, from a normal distribution. But we need to look at this point before we start putting things into the calculator. Are assumptions for this problem met? First of all, we have to have a random sample of American adults, and we do. The problem says we have a random sample. We also have to make sure the number of successes and failures is sufficiently large. Here there were 582 successes, 421 failures, and they're both greater than 10, so we're in good shape there. And we also have to make sure we have a large population, and we do. This survey is about American adults, and there's certainly a large population there. So at this point, we could start to compute things by hand, but we are going to use our calculator for this. So here's our trusty calculator, and here's where we're going to go. We're going to go to the stat menu again. Under the stat menu, you're going to go over to tests, and we're going to look at the one proportion z test. We have one proportion in this problem, and we are using normal distribution procedures in order to compute a z value here. So the numbers you're going to have to put in is you're going to have to put in the null hypothesis, which is 0.5 for a proportion. We have 582 successes out of 1,003 people who were in the sample. And you have a choice between calculate and draw. I like draw because it gives you a nice picture of what's going on. And here's what our calculator gives us. It gives us a picture of the results, and we want to make sure we understand what's going on here. So keep in mind the middle is 0.5 and 0.58 is out here, and nothing's shaded because 0.58, according to the calculations, happens to be 5 standard deviations away. And we've learned in class that 5 standard deviations is a pretty unusual occurrence. So that's why we really don't see anything shaded here. But we do want to pay attention to that z test statistic, which is 5.08. And we also want to make note of the p-value, which here it's not exactly 0, but it's essentially 0. 5 standard deviations is really far out there. So we can say with pretty much good confidence that the p-value is essentially 0 here. And this would indicate to us that we have a very unusual result. That getting a result of 58% when we should expect 50% is a very unusual result and is going to cause us to reject the null hypothesis. So what do we do with all this? So the p-value is less than our alpha, which was 5%, and we're going to reject the null hypothesis. This is evidence that we're not unlucky people here, that having something that would occur basically never, because the p-value is 0, causes us to believe that the 0.5 that we were using to compute things is an incorrect statistic. So we are going to conclude the alternate hypothesis, and we will conclude that the true proportion of American adults who look at the food labels is actually greater than 0.5. So from beginning to end, that's how we do one of these problems. So let's look at a second problem here. And this one is about graduation rates. We're comparing one particular state's graduation rates to the entire country. And here we see that the national proportion is 61%, and in this particular state it is 58%. So the population of interest is the proportion of students in this particular state who graduate high school and attend college. That's what we're looking at here. And we want to know if this state is somehow different than the rest of the country. So let's walk through all the procedures here. We have a null hypothesis that the proportion in the state should be 61%. Now here's something interesting happens. The alternate hypothesis is actually going to be is greater than or equal to. It's different than 0.61. We don't know if the proportion is greater than, less than. We didn't have a suspicion at the beginning of the problem. We just thought it somehow might be different. Whenever you hear that word different, you want to use the not equal to notation here. So we're saying that the proportion will be something different than 0.61%. So we have a random sample. Let's walk through all the assumptions. We have a random sample. Number of successes and failures was greater than 10, and we do have a large population. We're going to use an alpha of 0.01 because that's what this problem asks for here. So if we end up with a p-value of less than 1%, we will have proven a cause and effect relationship here, and we will reject the null hypothesis. So I draw a little sketch here, and notice I've sketched both sides because the alternate hypothesis is not equal to. That means that we're looking for a result that is as unusual as this in either direction. So we have to shade both sides. So I used my calculator here, and the z-score came out as negative 2.38, and we had a p-value of 0.017, and we know that 0.017 is not less than our alpha, which is 0.01. So we're not going to reject the null hypothesis. That means we're saying that while our results here are unusual, that 61% is certainly 58% rather is certainly different than 61%. It's not different enough for us to reject the fact that 61% might actually be the true proportion for kids in the state. So we're not going to reject the null hypothesis, and we cannot conclude that the true proportion that the state differs from the actual proportion of 61%. So that's walking you through two problems. I suggest you take a look at the problems in the book. Come ready for class next time with questions you might have, and we'll walk through a problem in class. But this takes care of problems concerning population proportions and hypothesis tests for them.